Hello and good day. This presentation presents our RTL design for the automatic filling and batching controller. Our system automates batch processing by using a programmable threshold and batch size. The controller waits for a data_valid signal, accumulates the batch weight, and performs a real-time threshold comparison. Once the target is reached, the system asserts a done flag to stop the process. To ensure reliability, we implemented an FSM-plus-D architecture, clearly separating the control unit logic from the Datapath arithmetic. This approach provides a modular, easily verifiable design that meets all performance requirements. We will now walk you through our architectural design and simulation results.
Hello, I will explain the RTL ACM chart of our automatic filling and batching controller. The controller begins in state 0, which is the IDLE or receipt state. Whenever the receipt signal is activated, the controller returns to this state and waits for the user to press start buttons. A decision box checks the start button. If start equals 0, the controller remains in state 0 and continue waiting. One start becomes 1, controller proceeds to state 1. In state 1, the controller initializes the system by clearing the running tool register represented by RT and setting the done signal to 0. This ensures that every filling cycle starts from a clean state. Then the controller moves to state 2. In this state, two important values are loaded into the Datapath. First, the fixed batch size, which is 25 gram, is loaded into the register R1. Second, the user programmed threshold value is loaded into register R2. These values remain available through the filling process. Next, controller enters state 3, where it waits for data valid signals. This signal indicates that one complete dispensing operation has finished successfully and that a full 25 gram batch is ready to be added. If data valid is 0, the controller remains in state 3 and continues waiting, preventing incomplete or unstable measurements from being proceeded. Once data valid becomes 1, the controllers move to state 4. In this state, the database performs the accumulation process. The controller updates the running total by adding the batch size to the previous total. In other words, the operation is performed, total is equal to total plus batch size. Immediately after updating the total, the controller compares the new total with the programmed threshold. If the total is still less than the threshold, the decision output is 0, and the controller returns to state 3. Finally, in state 5, the controller asserted the done signal by setting done equals to 1, indicating that the required amount has been successfully accumulated and the filling process is completed. After compilation, the controller returns to state 0. Next, I will explain about the Datapath unit, which is responsible for performing the arithmetic operation and storing the data during the filling process. On the left side of the Datapath, there are two registers. Register 1 stores the fixed batch size, which is in our project is 25 gram. And register 2 stores the programmable threshold value by entered by the users before the process starts. Both registers are loaded using the control signals of LD1 and LD2 generated by the control unit. The output of register 1 passes through a multiplexer controlled by the SELY signal. These multiplexers allow the database to either pass batch size or 0 value. The selecting 0 is useful during initialization or when the controller wants to prevent any addition from occurring. The selected value is then sent to the adder, where is added to the current running total stored in the total register. The adders perform the operation. New total is equal to current total plus batch size. As you can see, the output of the adder then passes through another multiplexer controlled by TCLR signal. During reset or initialization, the multiplexer selects 0 so that the total register is cleared. Otherwise, it selects the other output, allowing the running total to be updated. The updated value is then stored inside the total register, which keeps tracks of the accumulated amount throughout the filling process. Next, the total is sent to a comparator, where it's compared with the threshold value stored in register 2. The comparator checks whether the accumulated total is greater than or equal to the programmable threshold. The comparator generates the output signal Z when Z equals 0. The total has not yet reach the threshold, so another batch is required. When Z equals 1, the required amount has been reached or exceeded, and this signal is sent back to the control unit. Then I will move to the control unit design, which is control the sequence of operation performed by the Datapath. The control unit is implemented as a finite state machine consisting of 3 main blocks: the next state logic and the present state register and the output logic. The next state logic receives the external input, start data, and the comparator output Z from the database based on these signals and the current state. It determines what the next state of the controller should be. The calculated next state is stored in the present state. This register is updated on every rising edge of the system clock. It also receives the reset signals, which immediately forces the controller back to the initial IDLE state whenever reset state is activated. The current state is stored in the present state. Register is then sent to the output logic. The output logic generates all the control signals required by the data path. These control signals include LD1, LD2, enables total register to store a new accumulated value, SELY, which controls the input multiplexer before the adder, TCLR, which clears the total register during initialization, and finally the done signals, which indicate that the required threshold has been reached. During operation, the control unit continuously monitor the data valid signal to determine when the new batch is ready, and it's monitored the comparator output Z to determine whether the accumulation process should continue or stop.
Moving on to the independent verification of our control unit FSM. At the start of the timeline, when reset is pulled high, the FSM initializes securely into the idle state, S0. As soon as reset drops and a high pulse is detected on the start signal, the FSM instantly moves forward. Clear and load execution states. We can observe the sequential execution immediately after the start pulse. First, the controller triggers a clear total phase where T_r and IDT pulse high to erase old Datapath data. On the very next clock cycle, the system moves to state S2, where ID1 and ID2 are asserted to latch our programmable batch size and threshold configurations, handling the wait loop and accumulation. The FSM then rests in state S3, waiting for sensor data. When the first data_valid pulse arrives, the controller transitions to state S4 to perform an addition and threshold check, pulling SELY and IDT high. Because the status signal Z remains low, indicating the target is not yet met, the FSM gracefully loops back to the wait state. Target achievement and done signal. Finally, when the subsequent data_valid pulse arrives and the datapath flag Z switches to high, the FSM successfully detects that the threshold has been reached. It instantly branches to state S5, where it asserts our top-level external done signal for exactly 1 clock period before returning to idle. This confirms flawless operational logic. Next, we verify the datapath unit. As we've designed, the DU is the computational core of our system, containing the batch size register, the threshold register, and our running total register. In this simulation, we first clear the total register by asserting T_r and IDT. We then load the datapath with our test parameters, a batch size of 30 and a threshold of 80. Watch how the registers capture the data exactly when the load signals ID1 and ID2 are high. This proves that our storage hardware is accurately latched to the system clock. The most critical part of the DU is the look-ahead comparator. As we step through the accumulation pulses, the adder updates the running total. On the third accumulation cycle, the hardware computes 90, which is greater than our threshold of 80. You can see the status signal Z flip high immediately, even before the clock edge, confirming that our combinational logic is perfectly synchronized. Finally, we verify the full integrated system. By binding the control unit and datapath unit together at the top level, we create a complete autonomous filling controller. Our test bench applies the same 25-unit batch size and 100-unit threshold to ensure end-to-end functionality. Upon triggering the start signal, the system automatically sequences through initialization and configuration. We then apply 4 discrete pulses to the data_valid input. You can observe the accumulated total inside the system rising in perfect steps of 25, remaining stable and ignoring input noise whenever the sensor data is low. On the 4th pulse, the accumulated total hits 100. The system immediately satisfies the threshold condition, and on the very next clock cycle, it asserts the done signal high. This confirms that our FSM-plus-D architecture is robust, timing accurate, and meets all design specifications for the assignment. This concludes. In summary, our group has successfully designed and implemented an automatic batching controller that satisfies all specified system requirements. By strictly adhering to the FSM-plus-D methodology, we achieved a modular design that is both efficient and easy to verify. Our simulation results across all test benches confirm that the system correctly manages configuration parameters, handles sensor-based batch accumulation, and triggers the completion signal exactly when the threshold is met. The top-level integration proves that our control and datapath blocks work in perfect synchronization. This project has not only deepened our understanding of RTL design and state machine synthesis but has also reinforced the importance of rigorous simulation and timing analysis in digital hardware development. Thank you for your time, Doctor. This concludes Group 17's presentation for Assignment 2.